Hey friend, tonight we're going to explore the invisible scaffolding of the universe, the hidden geometry that shapes space, time, and reality itself. So get comfortable, let your thoughts float free, and let's drift together into a world where particles vanish, space bends, and dimensions unfold quietly in the dark. Chapter 1. What is quantum space? What does it mean to exist in space? In our daily experience, space feels familiar. It's the empty stage upon which matter moves and time unfolds. You can walk across a room, reach out to touch an object, or point to the location of a star in the sky. Space, in this intuitive view, is simply the container of the universe, a passive backdrop. But quantum physics dismantles this picture piece by piece. When we descend into the microscopic realm of particles, waves, and uncertainty, space becomes something far stranger than an empty void. In the quantum world, space is no longer a static arena. It becomes a dynamic participant, a structure that resists classical intuition and challenges our most basic assumptions about what it means to be somewhere, or even to exist at all. In classical physics, space is described through geometry, the geometry that emerged from the legacy of Euclid and evolved through Newton's mathematical formalism. Newton's space was absolute, eternal, and uniform. Objects moved within it according to deterministic laws, and their positions and momenta could, in principle, be known with perfect accuracy. Even after Einstein redefined space in the framework of general relativity as a curved, malleable fabric shaped by mass and energy, the idea that particles had definite locations in space persisted, albeit within a flexible, gravity-sensitive medium. But quantum mechanics reimagines the very concept of location. In quantum theory, a particle does not have a single, well-defined position. Instead, it exists in a probabilistic cloud of possible positions. This is not a limitation of our measurement tools, but a fundamental property of reality itself. The wave function, a core concept in quantum mechanics, describes the probability amplitude of finding a particle in a particular region of space. And unlike classical probability, which describes ignorance, quantum probability arises from the intrinsic nature of quantum systems. To describe where quantum objects are, physicists turn to an abstract mathematical structure called Hilbert space. Unlike the familiar three-dimensional physical space, Hilbert space can have infinitely many dimensions. Each possible state of a quantum system corresponds to a point in this space, not a specific position in the physical world. For a single particle moving in one dimension, the wave function itself is an element of a Hilbert space, an infinite dimensional space of square integrable functions. These functions don't simply tell us where the particle is. They represent a superposition of all the places it could be, all at once, until a measurement collapses that possibility into a single outcome. This leads to an important shift in understanding. In classical physics, space is a given, and particles are placed within it. In quantum mechanics, space is not a stage, but an emergent property of how we describe and observe quantum systems. The particle doesn't exist in space in the traditional sense. Rather, its wave function spans potentialities, mathematical constructs that don't require a classical backdrop. It is only through the act of measurement that a specific spatial location is realized. Until then, location is not just unknown, it is undefined. This probabilistic nature of position can be illustrated by the famous double-slit experiment. When a single particle, such as an electron, is fired toward a pair of slits, and no measurement is made to determine which slit it passes through, it behaves as though it travels through both slits simultaneously. The resulting interference pattern on the detection screen is not the behavior of a particle localized in space, but that of a wave-like entity spanning multiple possibilities. Only when we introduce a measurement that pinpoints the path does the interference vanish, and the electron appears to travel through one slit or the other. This experimental result highlights the deeply non-classical behavior of space at the quantum level. The geometry we think of as spatial location is not a fixed feature of the particle's existence, but a relational result of how we choose to observe it. Even more curiously, space itself may not be fundamental. In certain interpretations and extensions of quantum theory, space and time are seen as emergent from more basic entities, such as quantum information or entanglement patterns. This perspective is radical, but gaining traction. In particular, when attempting to unify general relativity with quantum mechanics into a theory of quantum gravity, many researchers propose that space might be a consequence of how quantum states relate to each other, rather than a basic component of reality. Entanglement provides one clue to this deeper structure. When two particles become entangled, their combined wave function cannot be written as a product of individual states. This non-local connection challenges the classical view that objects can only influence each other through interactions in space. In a quantum framework, correlations between particles exist regardless of spatial separation. Some physicists now propose that the strength and structure of entanglement between parts of a system might be what gives rise to the appearance of geometric space in the first place. That is, distance may be a measure of quantum disconnection, not of physical separation. Recent theoretical developments explore this possibility in detail. For instance, in research inspired by the ADS-CFT correspondence, a conjecture from string theory, scientists propose that the geometry of space may arise from entangled quantum bits in a lower dimensional system. The idea is that space, and perhaps even gravity itself, could be the emergent result of an underlying network of quantum entanglements. In this view, geometry is not primary, but a shadow of more abstract relational data. What we interpret as curvature, distance, and dimensionality may all be built from how these fundamental elements are linked. Such ideas invite a re-evaluation of what space is. Is it just a convenient language to describe classical limits of quantum mechanics? Or is it something more, a derived feature of an even deeper reality? From this standpoint, physical space as we know it is perhaps like a shadow, emerging from a richer, more abstract mathematical reality that defies classical comprehension. Another profound implication arises when we consider the quantum vacuum. In classical physics, a vacuum is simply empty space, devoid of matter and energy. But quantum field theory, the marriage of quantum mechanics and special relativity, paints a very different picture. In this view, even empty space is a teeming landscape of activity. Quantum fields pervade all of space, and particles are merely excitations of these fields. What we think of as the vacuum is actually the lowest energy state of these fields, a state that still experiences fluctuations due to the uncertainty principle. These fluctuations are not just theoretical curiosities, they have measurable consequences. For example, the Casimir effect, where two uncharged metal plates placed very close together experience an attractive force, arises directly from differences in quantum vacuum energy. The geometry of space at this level becomes highly non-trivial. It is no longer enough to imagine smooth, continuous surfaces. Instead, we must grapple with a restless, probabilistic foam, a seething structure of potentialities and fleeting realities. This is the quantum world's version of geometry, not clean lines and fixed points, but complex amplitudes, probabilistic overlaps, and ever-shifting topologies that only become tangible when observed. In some speculative models of quantum gravity, space might be composed of discrete units, tiny building blocks that encode information about volume, area, and curvature. Loop quantum gravity, for instance, proposes that space is quantized, made up of loops forming a spin network that defines the geometry of the universe at the smallest scale. In this framework, continuous space breaks down into a granular structure, where the smoothness we experience is merely an approximation that emerges at large scales. The very idea of distance or location becomes subject to the underlying connectivity of these discrete units. These approaches, whether through fields, loops, or entanglement networks, reflect the growing realization that space is not the quiet emptiness it once seemed. It may be a dynamic, emergent, and even illusory phenomenon born from deeper principles that we are only beginning to grasp. And if space is not fundamental, then our notions of distance, direction, and separation may all be contextual illusions, artifacts of our limited perspective within a vast and strange quantum structure. This strange new conception of space challenges more than physics. It touches on questions that border philosophy. If space isn't fundamental, what does it mean to be somewhere? If location itself is emergent from entanglement or abstract mathematical relations, then the boundary between subject and object begins to blur. Are we not then part of the very structure we're trying to observe, woven into the geometry rather than merely residing in it? In the end, perhaps the most humbling truth of quantum space is this: it resists being visualized, categorized, or fully known. It operates beyond the framework of human intuition, which was shaped by a macroscopic world where space feels rigid and real. Yet at the deepest level, space may be more like a suggestion, a soft scaffold of relational probabilities that shift and shimmer as we observe them. We look for a floor to stand on in the quantum world, and we find only a mirror of our own questions. Chapter 2. The Hilbert Space, Where Quantum Lives. When we speak about space in the quantum realm, we do not mean the familiar three-dimensional world we navigate in daily life. Instead, the concept of space undergoes a radical transformation. It becomes something abstract, mathematical, and deeply rooted in the formalism of quantum theory. At the heart of this new understanding is the concept of Hilbert space. It is not a place in the traditional sense, not a realm filled with particles and fields, but rather a framework for describing all possible states a quantum system can occupy. If classical space is where particles reside, Hilbert space is where the very possibilities of those particles live. It is the fundamental setting for quantum mechanics, and understanding it is essential for grasping the structure of the quantum world. Hilbert space is a complete vector space equipped with an inner product. Each vector in this space represents a quantum state, and the mathematical rules that govern these vectors mirror the physical rules that govern quantum systems. The completeness of Hilbert space means that it contains all limits of converging sequences of vectors, ensuring that physical predictions remain consistent and well-defined. Unlike classical three-dimensional space, Hilbert space can be infinite-dimensional. This is necessary to accommodate systems with an infinite number of potential states, such as a particle moving freely along a line or a harmonic oscillator with an unbounded energy spectrum. Why are quantum states vectors at all? The answer lies in how quantum systems behave and how we describe them. Quantum mechanics is a linear theory. The superposition principle, a core idea in the field, states that if a system can be in one state and also in another, it can also be in a linear combination of both. This property naturally aligns with the structure of vector spaces, where linear combinations of vectors yield new vectors within the same space. In this context, each possible quantum state is a vector, and the act of combining them through superposition reflects the probabilistic and undetermined nature of quantum outcomes. These vectors are not tied to positions or momenta in physical space. Instead, they represent the total information available about a quantum system. This includes properties like spin, polarization, energy levels, or even the entanglement between subsystems. A single quantum state vector in Hilbert space contains all the amplitudes associated with every possible measurement outcome. It is this mathematical abstraction that allows quantum theory to describe systems with extraordinary flexibility, whether it's an atom in a trap, an electron orbiting a nucleus, or a photon traveling through an interferometer. One of the most striking features of Hilbert space is its dimensionality. In classical mechanics, the state of a system is fully determined by a finite number of variables, such as position and momentum. These variables exist in phase space, which has a fixed number of dimensions depending on the system's degrees of freedom. But in quantum mechanics, the number of dimensions is typically infinite, especially for continuous systems. A particle on a line, for example, requires an infinite dimensional Hilbert space to represent all possible positions and momenta it might have. Each dimension in this space corresponds not to a direction in real space, but to an amplitude associated with a basis state. To make sense of this abstract structure, physicists define orthonormal basis vectors, states that are mutually exclusive and collectively exhaustive. Just as any vector in three-dimensional space can be expressed as a combination of unit vectors along the x, y, and z axes, any quantum state can be expressed as a sum over basis vectors in Hilbert space. These basis states are typically chosen to correspond to measurable quantities, like position or energy levels. The coefficients in this expansion, the probability amplitudes, contain the information about the likelihood of observing each outcome if a measurement is made. Crucially, the inner product in Hilbert space gives physical meaning to these vectors. The inner product between two state vectors determines their overlap, or in probabilistic terms, how similar or different they are. The square of the magnitude of the inner product gives the probability that a system in one state will be found in another if measured. This mathematical operation encodes the fundamental rule for calculating quantum probabilities, known as the Born rule. It is through this rule that Hilbert space connects to reality, translating abstract amplitudes into observable frequencies of outcomes. This structure also explains why quantum mechanics is inherently probabilistic. Even if we know the exact quantum state of a system, its precise vector in Hilbert space, we can only predict the probabilities of different measurement results, not the outcomes themselves. The act of measurement selects a particular basis in Hilbert space, collapsing the state vector into one of the basis states and thereby giving a definite outcome. But before the measurement, the system is described by a superposition, a vector that stretches across many possibilities. Moreover, Hilbert space allows us to describe composite systems in a rigorous way. When two quantum systems are combined, their joint state lives not in a simple addition of individual spaces, but in the tensor product of their Hilbert spaces. This mathematical operation creates a much larger space that includes not only the individual states of each system, but also their entangled combinations. These entangled states cannot be factored into separate parts. They exist only in the joint space, reinforcing the idea that quantum systems are deeply interconnected at a fundamental level. The abstract nature of Hilbert space might seem distant from reality, but its predictive power is unmatched. Quantum theory, formulated entirely within this mathematical space, has passed every experimental test for over a century. From the energy levels of hydrogen to the behavior of semiconductors, from superconductors to quantum computers, the vectorial structure of Hilbert space underlies the most accurate physical predictions ever achieved. It governs the design of lasers, the functioning of MRI machines, and the precision of atomic clocks. Without Hilbert space, none of these technologies would be possible. Interestingly, Hilbert space also provides a foundation for new quantum technologies, including quantum computation and communication. In quantum computing, for example, each qubit corresponds to a two-dimensional Hilbert space, and the power of a quantum processor grows exponentially with the number of qubits because the total state space becomes a high-dimensional tensor product. This immense Hilbert space allows quantum algorithms to explore many computational pathways simultaneously, leading to speed-ups in tasks like factoring, searching, and simulating physical systems. In quantum cryptography, Hilbert space is what guarantees the security of communication. The no-cloning theorem, which states that an unknown quantum state cannot be copied, is a direct consequence of the linear and vectorial nature of Hilbert space. This property ensures that any attempt to intercept or measure quantum information will disturb the system and reveal the presence of an eavesdropper. Despite its utility, Hilbert space remains difficult to visualize. We cannot picture it in the same way we imagine physical space. Its dimensions are not spatial but abstract, defined by complex numbers and linear relationships rather than geometric distance. This lack of visualization should not be mistaken for lack of reality. Just as we accept higher dimensional mathematical constructs like phase space in classical mechanics or curved spacetime in general relativity, Hilbert space is a real and indispensable component of our best description of nature. One might wonder whether Hilbert space is merely a mathematical tool or if it has ontological status, whether it is reality or merely represents it. This question sits at the intersection of physics and philosophy, and opinions vary. Some interpretations of quantum mechanics, such as the many-worlds interpretation, treat the universal wave function, an object in a vast Hilbert space, as the true state of the universe. In this view, every possible outcome of a quantum event corresponds to a branch of the wave function, all coexisting in the abstract expanse of Hilbert space. Other interpretations, such as cubism, treat the wave function as a tool for organizing an observer's beliefs about the world rather than a physical entity. Regardless of interpretation, Hilbert space remains the canvas upon which quantum theory is painted. It defines what it means for a system to exist, to evolve, and to be measured. Time evolution in quantum mechanics is described by unitary transformations, rotations in Hilbert space that preserve the inner product and thus the total probability. These transformations, governed by the Schrödinger equation, trace smooth paths through this abstract space, connecting the state of a system at one time to its state at another. All of this suggests a reality that is deeply structured, not in terms of particles in motion through space, but in terms of amplitudes evolving in a vast, invisible landscape. Hilbert space is not empty. It is rich with possibility, and every quantum system dances through it, tracing a path not through physical distance, but through potential and probability. And so we arrive at an unsettling but quietly beautiful realization. We are part of a universe built not from solid matter moving through empty voids, but from evolving patterns in an infinite space of possibilities. The solidity we feel, the positions we see, the separations we imagine, all arise from vectors drifting through a domain we cannot see but must believe in. In that unseen dimension, the world exists not as it is, but as it might be. Chapter 3. Superposition as Spatial Geometry. To grasp the surreal behavior of the quantum world, one must first abandon the need for certainty and replace it with a vocabulary of possibility. Nowhere is this more evident than in the principle of superposition. At its core, superposition is not merely a feature of quantum mechanics, it is its essence. It explains how particles can exist in multiple states simultaneously, how probabilities evolve with time, and how information flows through the quantum universe. But beneath this seemingly abstract idea lies a deep and beautiful structure, one that is profoundly geometric. To understand superposition is to understand how the fabric of quantum space is stitched together by vectors, angles, and amplitudes. In the classical world, systems occupy definite states. A coin is either heads or tails. A switch is either on or off. But in quantum mechanics, a system can exist in a state that is not one or the other, but both simultaneously. This is not a metaphor. It is a precise mathematical reality described by the addition of vectors in Hilbert space. If one state vector represents a coin being heads and another vector represents tails, the quantum system can exist in a state that is the sum of those vectors. The result is a new state, distinct, unique, and containing the potential for both outcomes, yet committing to neither until observed. This is vector addition in its most profound form. When we add quantum states, we are not simply combining outcomes. We are combining the very potential for outcomes. The likelihoods, the phases, the structural information about what the system could reveal if we ask it a question. In Hilbert space, each vector is defined not only by its direction, but also by a complex amplitude. These amplitudes encode both magnitude and phase. And it is this phase that gives quantum mechanics its most counterintuitive and powerful features. When two state vectors are added, their amplitudes interfere. Unlike classical probabilities, which always add positively, quantum amplitudes can cancel each other out. Two possibilities can subtract rather than reinforce. This is not due to error, nor due to a lack of information, but due to the underlying geometry of quantum states. Constructive interference occurs when phases align, enhancing the probability of a given outcome. Destructive interference happens when phases oppose each other, reducing or eliminating the chance of that outcome. This interference is not an artifact of measurement. It is built into the structure of the wave function itself. One of the most striking examples of this interference emerges in the famous double-slit experiment. When a single particle, such as an electron, is directed at a pair of slits, and no measurement is made to determine which slit it passes through, it does not act like a classical particle. Instead, it behaves like a wave, interfering with itself. The particle's wave function spreads through both slits and interferes in the space beyond them, producing a pattern of alternating high and low probabilities on the detection screen. Some regions show high likelihoods where constructive interference occurs, and others show low or zero likelihoods where destructive interference cancels out the amplitude. This pattern reveals a deeper truth. The electron was in a superposition of paths, and its spatial behavior is dictated not by one path or another, but by all paths. simultaneously interacting within the geometry of its state. In a geometric sense, superposition is the phenomenon that allows a single vector to point in multiple directions at once. This is not possible in classical vector spaces, but in Hilbert space, the notion of direction includes not just orientation, but also internal quantum phase. It is this phase that enables multiple realities, each encoded by a component of the superposition, to coexist within a single unified state. To make this abstraction more intuitive, physicists often rely on simplified geometric models. One of the most powerful is the block sphere, a conceptual tool used to visualize the state space of a qubit, the basic unit of quantum information. A qubit is not like a classical bit that is either 0 or 1. Instead, it can exist in a superposition of 0 and 1, described by a point on the surface of a sphere. The north pole of the sphere represents the pure state 0, and the south pole represents 1. Any other point on the sphere's surface corresponds to a linear combination, a superposition of those two basis states. The latitude and longitude on the block sphere correspond to the relative amplitudes and phases of the state. A qubit at the equator, for example, is in an equal superposition of 0 and 1, but depending on its angle around the equator, the phase between these components changes. This phase difference has real consequences. It determines how the qubit will evolve in time and how it will interfere with other qubits. Through this geometric model, we see how superposition is not just a vague overlap of possibilities. It is a specific, structured state, encoded by a location on a complex surface. The block sphere captures this by representing every pure state as a point, and every operation on a qubit as a rotation in three-dimensional space. However, it is important to remember that the block sphere is a simplified case. Most quantum systems cannot be visualized so easily. While a single qubit lives on the surface of a sphere, two qubits already require a much more complex, higher dimensional space to describe all possible states and entanglements. Superpositions in such systems span exponentially larger Hilbert spaces, making geometric visualization impossible. But the principles remain the same. Every state is a vector. Every vector is a superposition. And the geometry of these vectors governs the physics we observe. The structure of superposition also explains why quantum computers are so powerful. In a classical computer, each bit exists in one of two states, but in a quantum computer, each qubit exists in a superposition of both. When many qubits are entangled, the system evolves through a high-dimensional space, with each dimension corresponding to a possible configuration of the system. The ability to explore all of these configurations simultaneously allows quantum algorithms to perform tasks that classical systems struggle with. But this computational power is not magic. It arises from the same geometric rules of vector addition and interference that govern a single electron passing through a slit. Superposition also plays a central role in quantum measurement. When a measurement is made, the system appears to choose a particular outcome. But this is not because the system had a hidden state all along. Instead, the act of measurement selects a particular basis in Hilbert space and projects the state vector onto one of the basis vectors. This process, called wave function collapse, reduces the superposition into a definite outcome, but only in that basis. In a different basis, the system may still be in a superposition of different possibilities. This basis dependence underscores the fact that superposition is not just a feature of the system, but of how we describe and interact with it. The mathematical precision of superposition contrasts sharply with its philosophical implications. A system in superposition does not contain hidden variables waiting to be revealed. Instead, it genuinely exists in a state of potential, a state that embodies multiple possibilities at once. This defies our everyday experience, in which things appear definite and exclusive. But at the quantum level, definiteness only arises through interaction. Before we ask the question, the system holds every answer. After we ask, we get only one. This has profound implications for our understanding of reality. It suggests that the world is not made of things, but of relationships, of angles, amplitudes, and overlaps in a vast geometric space. A particle is not a tiny object with a location, but a vector sweeping through Hilbert space, guided by the rules of linearity and interference. What we perceive as physical behavior is, in fact, the projection of this higher dimensional dance onto the limited surface of human experience. If the universe is a computation, then superposition is its language. If the cosmos is a structure, then superposition is its scaffolding. And if reality is a process, then superposition is its pulse, the gentle trembling of all that could be, waiting for something or someone to look and decide. Chapter 4. Entanglement and Nonlocal Geometry. When two particles become entangled, something remarkable happens. Their individual identities, in the quantum sense, dissolve into a shared existence. Entanglement is not merely a connection between two distinct particles. It is the formation of a new holistic quantum state that cannot be described in terms of its components alone. The mathematical language that expresses this profound unification is the tensor product. In quantum theory, this operation is used to combine the state spaces of individual systems into a single, larger state space, one that contains both the individual possibilities and, crucially, their interwoven correlations. To appreciate the geometry of entanglement, we must first understand how state spaces scale. For two classical systems, combining them is straightforward. Each one retains its identity, and their combined state is just a list of their respective states. But in quantum mechanics, the combination of systems is richer and more complex. Each quantum system is represented by a Hilbert space. When two systems are considered together, their joint state lives in the tensor product of their individual Hilbert spaces. This means that even if the individual spaces are finite dimensional, their combination grows exponentially. A pair of two-level systems, or qubits, for instance, does not yield four classical combinations. It creates a new four-dimensional space capable of hosting states that are fundamentally non-separable. This tensor structure is not just a convenient way to organize information. It is essential for describing quantum correlations. Entangled states are those which cannot be written as a product of individual state vectors. They are not merely mixtures or statistical combinations of two systems, but new, unified states that exhibit non-classical correlations across space and time. Geometrically, entanglement implies that the direction of the joint state vector in this higher dimensional space cannot be decomposed into directions in the individual subspaces. It points into a region of Hilbert space that is inaccessible to separable states. To make this more concrete, consider the Bell states, the canonical examples of maximally entangled two-qubit systems. These states live in the four-dimensional tensor product space of two qubits, and each represents a quantum state with perfect correlations. For example, in one of the Bell states, the measurement outcomes of both qubits are perfectly correlated. If one is measured in a given basis and found to be in a certain state, the other will always be found in the matching state, even if separated by vast distances. But what's crucial is that prior to measurement, neither particle has a definite state of its own. It is only the pair, described as a whole, that possesses a well-defined quantum identity. This is where the geometric intuition begins to shift. In classical space, distance defines separation. Two objects located at different positions have independent properties, and any correlation between them must be explained by local interaction or causal history. But in quantum mechanics, entanglement implies that correlation exists without spatial mediation. The geometry of these correlations is not embedded in the fabric of physical space, but in the structure of Hilbert space. In other words, two particles can be far apart in three-dimensional space, yet be close, intimately connected in their shared state vector. This non-local geometry defies classical metaphors. A useful, though limited way to imagine it is to picture entangled states as stretching across a hidden dimension, one that is orthogonal to the familiar directions of up, down, left, and right. In this hidden dimension, the two particles are adjacent points on a single structure. Their separation in physical space becomes irrelevant to their quantum relationship. The connection exists in correlation space, a landscape defined not by meters or kilometers, but by vector alignment in Hilbert space. Importantly, this connection does not allow for faster-than-light communication. The correlations manifest only when both measurements are made and their results are compared. No information is transmitted directly between the entangled systems. Nevertheless, the existence of these correlations, confirmed repeatedly in laboratory experiments, suggests that the quantum world is governed by a deeper kind of order, one in which the classical notion of distance is secondary to a more fundamental concept of quantum proximity. In experiments that test Bell's inequalities, the predictions of quantum mechanics diverge sharply from those of any theory based on local realism. These inequalities are derived under the assumption that measurement outcomes are determined by pre-existing properties, realism, and that these properties are not influenced by events outside their local region, locality. But quantum mechanics violates these inequalities, and experiments consistently confirm the quantum predictions. This empirical violation forces us to rethink how the universe is wired together. The geometry of entanglement does not fit within the confines of any classical blueprint. It suggests a structure that exists independently of the coordinates we impose on it. This structure becomes even more intricate when we consider systems with more than two entangled particles. In multi-particle entanglement, the tensor product space becomes vastly more complex, allowing for a wide array of correlation patterns. These patterns are not reducible to pairwise interactions. They represent higher-order entanglements, situations where the global state is entangled, but no two particles within it are necessarily entangled with each other. These so-called GHZ states and W states, among others, occupy geometrically distinct regions of the composite Hilbert space. Their study is central to quantum information theory, where entanglement is not just a curiosity, but a resource, something that can be quantified, manipulated, and consumed. As we expand this view further, some researchers propose that space itself may emerge from entanglement. In certain quantum gravity approaches, such as those inspired by the Holographic Principle or tensor network models, the geometry of space is built from patterns of entanglement between fundamental degrees of freedom. The distance between 2 points is no longer a primitive concept, but one that arises from how much entanglement exists between them. In these frameworks, space-time is not a background, but a derived concept, a manifestation of deeper quantum relationships. This perspective has led to a growing belief that entanglement may be the glue that holds the universe together. It acts not across space, but beneath it, shaping the very fabric of what we perceive as distance, direction, and separation. If this is true, then physical space is a kind of shadow, cast by the deeper connectivity of entangled systems. The apparent locality of the classical world may be an emergent property arising from the decoherence of highly entangled quantum states as they interact with complex environments. And here we return to geometry, not the geometry of triangles and circles, but of complex vector relationships, phase angles, and tensor structures. In this geometry, proximity is defined by correlation, not position. Two systems are close if their state vectors share components, if their joint state is entangled. They are far if they are statistically independent, regardless of how near they may be in physical space. This reshaping of geometry transforms how we think about everything from causality to identity, from the flow of information to the passage of time. This new geometry resists visualization. We cannot picture a 4- or 8-dimensional complex vector space, nor can we intuitively grasp the topologies of entanglement in large quantum systems. But we can calculate them, measure them, and verify their consequences. Entanglement entropy, mutual information, and fidelity metrics all serve as tools to chart the shape of this invisible terrain. The results are real and repeatable, even if the landscape they describe lies beyond our sensory reach. In practical terms, this geometry has applications across quantum technologies. Quantum teleportation relies on shared entangled states between sender and receiver. The entangled pair acts as a bridge, not across physical space, but through shared state space. Quantum key distribution uses entangled photons to ensure that any eavesdropping attempt disrupts the delicate correlations, providing an immediate signal of intrusion. In these applications, the geometry of entanglement is not just theoretical. It is operational, enabling new kinds of secure communication and information processing. And yet, even with all its rigor, entanglement remains deeply mysterious. What does it mean for two particles, separated by light years, to behave as if they are parts of a single system? How can correlations arise where no classical signal could have traveled? The answers may lie not in extending classical explanations, but in embracing the non-local geometry that quantum mechanics offers. A geometry where connection precedes separation, where wholeness emerges before parts, and where distance is not what it seems. Perhaps then entanglement is not simply a feature of the quantum world. Perhaps it is the quantum world, a place where relationships are more fundamental than things, and where the shape of what is possible extends far beyond the dimensions we can draw or the distances we can walk. In that hidden architecture, everything may already be touching, just not in the ways we're used to seeing. Chapter 5: Quantum Fields, Geometry in Motion. To truly understand the geometry of quantum space, we must move beyond the idea of particles as isolated, discrete entities. In the classical world, particles are thought of as point-like objects following predictable paths through space. But in the quantum world, this picture quickly collapses. Instead of particles, modern physics places its foundation on something more fundamental: fields. The framework known as quantum field theory, or QFT, replaces particles with continuous entities that extend across all of space and time. These fields are not static or passive. They are vibrant, restless, and dynamic, rippling with fluctuations even in their lowest energy states. In this view, space is not merely an arena for physical processes. It is itself an active, structured medium defined by these omnipresent quantum fields. In classical physics, fields are already familiar. The electric field and magnetic field, for example, assign a value to every point in space, indicating the strength and direction of force that would act on a charge. These classical fields are continuous and deterministic, governed by equations like Maxwell's that evolve smoothly over time. But in quantum field theory, the fields are not simply mathematical tools for describing forces. They are promoted to operator-valued entities, capable of creating and annihilating particles. Every particle we observe, electrons, photons, quarks, is an excitation of a corresponding quantum field. The field is the fundamental object, and what we call a particle is simply a quantized ripple in that field. This idea marks a profound shift. Rather than being embedded in space, the field is space, or at least inseparable from its structure. The geometry of quantum fields is encoded not in point particles, but in the way field values change across space and time. The field is a function defined over the space-time manifold, and its fluctuations determine everything from the propagation of light to the formation of matter. These fluctuations are not passive. They carry energy, momentum, and angular momentum, and they obey the rules of quantum mechanics. Every location in space hosts an infinite number of potential field configurations, and these configurations are what define the possible states of the universe. At the heart of this framework lies the notion of creation and annihilation operators. These mathematical objects act within Hilbert space, changing the number of particles in a given quantum state. They are not just formal devices, they represent physical processes. When an electron appears in a detector, it is because a creation operator has acted on the vacuum state of the electron field. When a photon is absorbed, an annihilation operator removes a quantum of excitation from the electromagnetic field. These actions are deeply geometric. They change the state of the field in ways that can be understood as transformations in the infinite dimensional space of field configurations. Each creation or annihilation event corresponds to a localized deformation in the field. In geometric terms, these operators map one point in Hilbert space to another, tracing a trajectory through the landscape of all possible field states. They alter the topology of quantum space, not in the visible three dimensions, but in the configuration space of fields. These operations are governed by algebraic rules that preserve the inner product structure of Hilbert space, ensuring that probabilities remain consistent. Yet the elegance of these rules hides the wild complexity beneath, the ever-changing dance of virtual particles, energy fluctuations, and probabilistic interactions that define reality at the smallest scales. This complexity is most evident in the quantum vacuum. In classical thinking, a vacuum is empty space, a volume devoid of matter or energy. But in quantum field theory, the vacuum is anything but empty. It is the ground state of the field, the lowest energy configuration consistent with the uncertainty principle. And yet, due to that very principle, the vacuum cannot be still. Even in its quietest state, the field fluctuates. These fluctuations are not abstract. They have measurable consequences. The Casimir effect, for instance, is a physical force arising from the difference in vacuum energy between two closely spaced conducting plates. It demonstrates that what we call nothing is actually seething with activity, a foam of transient excitations constantly appearing and vanishing beneath the threshold of detection. From this perspective, the vacuum becomes a geometric structure in its own right. It defines the baseline against which all field excitations are measured, and its properties shape the behavior of the universe. Different vacua correspond to different phases of the field, and transitions between vacua can drive cosmological processes such as inflation in the early universe or symmetry breaking in the formation of matter. The Higgs field, for instance, acquires a non-zero value in its vacuum state, giving mass to particles through interaction. This is not a background event. It is a field defining the structure of space itself, a silent geometry giving rise to everything we consider tangible. In the language of geometry, one can think of the vacuum as the origin of a vast coordinate system, an infinite dimensional space where each axis corresponds to a mode of the field. Excitations move the system away from this origin along specific directions, each associated with a particle species or interaction type. The operators that shift the system are like vectors pointing into different sectors of quantum possibility. And because these shifts are linear and governed by commutation relations, they preserve the symmetries of the underlying field. This symmetry structure, described by groups like SU2, SU3, and U1, is not merely mathematical. It encodes the conservation laws and interaction dynamics of the standard model of particle physics. But geometry here goes even deeper. In certain theories, such as gauge theories, the fields themselves have internal symmetries that vary from point to point in space. These local symmetries require the introduction of additional fields, gauge fields, that mediate forces. The curvature of these gauge fields, analogous to the curvature of space-time in general relativity, determines the strength and direction of interactions. This curvature is geometric in a precise sense. It reflects how field values twist and change across regions of space, forming a non-Euclidean structure even in flat spacetime. These geometric structures are not speculative. They are encoded in the very equations that predict particle interactions with astonishing accuracy. The standard model of particle physics, built on quantum field theory, accounts for everything from the magnetic moment of the electron to the decays of subatomic particles. Its predictions match experimental results to more than 10 decimal places. And at the root of this precision lies a world where particles are not things, but disturbances in a continuous, ever-present geometry, a tapestry of fields undulating across the vacuum. Even the idea of interaction is redefined in this framework. In classical terms, particles exert forces on one another by exchanging influence across space. In quantum field theory, interactions occur when fields overlap and interfere, when the combined geometry of multiple fields allows for the transfer of energy, momentum, or information. These interactions are encoded in the terms of a Lagrangian or Hamiltonian function, which governs how fields couple to each other. The process of quantization transforms these couplings into probabilities, and the resulting predictions describe everything from light scattering off atoms to the fusion of quarks into protons. Yet despite its success, quantum field theory remains incomplete. It cannot yet incorporate gravity in a consistent quantum framework, and its high-energy behavior leads to infinities that require careful renormalization. Still, these challenges do not diminish the profound insight it offers, that what we perceive as the material world is, at its foundation, a pattern of excitations in structured, fluctuating fields. This pattern is governed by symmetries, preserved by algebra, and animated by geometry. As we move toward the quantum theory of gravity and unified theories of physics, this geometric view of fields becomes even more essential. In some speculative frameworks, such as string theory, particles are not point-like but one-dimensional vibrations in higher dimensional spaces. These strings are excitations of underlying fields, and their geometry defines the spectrum of particles we observe. In other approaches, like loop quantum gravity, the very fabric of space-time is replaced by networks of quantized loops, linking geometry and quantum fields even more intimately. But regardless of the details, one message remains consistent. Space is not a void, and particles are not building blocks. The universe is composed of fields, and those fields are governed by a deep, hidden geometry, one that pulses beneath our perception, shaping everything we see, touch, and measure. And so we begin to glimpse a new picture of reality, one where emptiness is full, where movement arises from fluctuations, and where geometry itself flows through time. In this vision, we are not observers of a distant world, but expressions of a dynamic field, a standing wave in the quiet storm of quantum space. Chapter 6: Feynman Diagrams, the Geometry of Interactions. At the heart of quantum field theory lies a world of astonishing complexity. Particles are not objects traveling along well-defined paths, but are instead excitations in fluctuating fields that interact probabilistically. Yet for all its richness and abstraction, quantum field theory becomes tangible, almost visual, through one of the most elegant tools ever devised in theoretical physics, the Feynman diagram. These diagrams, named after physicist Richard Feynman, are not literal representations of particles in motion, nor are they simple cartoons. They are a form of geometry, a visual calculus for encoding and computing the probabilities of interactions. In their lines and vertices, they capture the essence of quantum electrodynamics and other field theories, offering a bridge between mathematical formalism and intuitive understanding. Feynman diagrams simplify the intractable by turning complex equations into visual maps. Each element of a diagram corresponds to a mathematical term in the perturbative expansion of a quantum field theory. Rather than solving enormously complicated integrals by brute force, physicists draw the structure of a process, assign mathematical rules to each part, and compute the result. This approach revolutionized quantum electrodynamics by allowing the calculation of scattering amplitudes with unprecedented clarity and efficiency. The basic structure of a Feynman diagram consists of particles represented by lines and their interactions represented by vertices. Time typically flows from left to right or from bottom to top, depending on convention, and the position along the diagram reflects the progression of a process. Straight lines usually represent fermions, such as electrons and positrons, while wavy or curly lines represent bosons like photons or gluons. Each vertex indicates a point in space-time where an interaction occurs, where one particle emits or absorbs another, or where particles annihilate and new ones are created. What makes Feynman diagrams remarkable is not merely their simplicity, but their geometric interpretation. Each diagram encodes a space-time trajectory. The lines are not physical paths in space, but expressions of quantum probability amplitudes, propagators, that connect points in the diagram. A propagator describes how a particle travels from one point to another, incorporating not just its motion through space, but all the quantum uncertainty and fluctuation along the way. These lines are like threads through Hilbert space, tracing the evolution of probability across space-time. At the interaction points, the vertices, quantum fields overlap and exchange energy and momentum. These are not collisions in the classical sense, but points where the field excitations interact, mediated by the symmetries and conservation laws that govern the system. In the case of quantum electrodynamics, an electron line might meet a photon line at a vertex, representing the absorption or emission of a photon. Each of these vertices contributes a specific factor to the total amplitude and the probability of the entire process is found by summing over all diagrams that contribute to the same physical outcome. These sums are not finite. In most realistic scenarios, an infinite number of Feynman diagrams must be considered, each with increasing complexity. Diagrams with only a few vertices are called tree-level diagrams and often provide a good approximation. But more accurate predictions require higher-order corrections, diagrams that include loops. A loop occurs when a line in the diagram bends back on itself, creating a closed path. These loops account for virtual particles, transient fluctuations that arise due to the uncertainty principle. They represent internal corrections to the process and are essential for achieving precise agreement with experiments. Loops introduce new challenges. The integrals associated with them can diverge, leading to infinities. However, these infinities can be managed through the process of renormalization, a mathematical procedure that adjusts the parameters of the theory to absorb the divergences. This is not merely a trick, but a consequence of the theory's structure, and it allows quantum electrodynamics to make predictions with astonishing precision. The electron's magnetic moment, for example, has been calculated and measured to match within a dozen decimal places, thanks to the careful inclusion of loop diagrams. Each Feynman diagram is more than a computational tool. It is a window into the nature of space-time and interaction. In a deep sense, the diagrams are geometric representations of how fields warp, connect, and influence one another across space and time. They show that interaction is not a single event, but a network of possibilities, an entangled mesh of causes and effects distributed probabilistically. And unlike classical geometry, which deals in definite shapes and trajectories, the geometry of Feynman diagrams operates in the space of amplitudes, complex numbers that encode phase, magnitude, and the interference patterns that arise from them. This geometrization is particularly powerful in quantum electrodynamics, where Feynman diagrams serve as the primary means of understanding electromagnetic interactions between charged particles. In this framework, photons are the mediators of the electromagnetic field. When two electrons repel each other, this repulsion is represented by the exchange of a virtual photon between their lines. The photon is not seen or measured. It exists purely within the internal structure of the diagram, a fleeting ripple in the field that connects the 2 points in space-time. More complex diagrams can show multiple photon exchanges, loops correcting the electron's self-energy, or even the creation of electron-positron pairs from the vacuum. These processes, though never directly observed in isolation, manifest in subtle corrections to energy levels and scattering angles. The Lamb shift in hydrogen and the anomalous magnetic dipole moment of the electron are both phenomena explained only by including these diagrammatic corrections. The beauty of Feynman diagrams is their adaptability. While originally developed for quantum electrodynamics, they have been extended to describe interactions in the strong and weak nuclear forces as well. In quantum chromodynamics, the theory of quarks and gluons, the diagrams become more elaborate due to the non-abelian nature of the gauge symmetry. Gluons, unlike photons, carry charge and can interact with each other, leading to a more intricate web of vertices and loops. Still, the geometric intuition holds. The particles are threads in a higher dimensional tapestry, woven together by field interactions. What emerges from this picture is a new way of thinking about space-time. Interactions are not localized collisions, but extended processes, smeared across the diagram and across the underlying quantum fields. The space-time coordinates associated with each vertex are integrated over, meaning that the process does not happen at a fixed point, but is distributed probabilistically across the continuum. In this sense, Feynman diagrams depict not the sequence of events, but the summation of all ways events could unfold. This perspective also aligns with the path integral formulation of quantum mechanics, where every possible history contributes to the total amplitude. A Feynman diagram is a distillation of this idea. Each line a collection of possible paths, each diagram a term in the grand sum over histories. The diagrams give us access to the geometry of quantum possibility, where every interaction is a fork in a multidimensional trajectory through field space. From a geometric standpoint, then, Feynman diagrams are not just tools, they are maps of quantum topology. They chart the routes taken by energy and information as they wind through the quantum fields. Their loops and vertices are not drawn on graph paper, but on the deeper canvas of configuration space, a terrain shaped by symmetry, uncertainty, and the rules of quantum evolution. In this space, position and momentum, time and energy are not separate axes but conjugate variables, entangled through Fourier transforms and governed by complementary principles. As we continue to explore more advanced field theories, those that attempt to unify all forces, including gravity, Feynman diagrams evolve as well. In string theory, for instance, interactions are not points connected by lines, but surfaces connected by tubes. The basic unit is not a vertex, but a junction of vibrating strings. Yet even here, the underlying idea remains that interaction is a geometry, and that this geometry encodes the dynamics of everything we see. Perhaps this is the most astonishing implication of all, that every event in the universe, every force, every collision, every transformation is ultimately a matter of geometry in motion. Not the static geometry of solid shapes, but a living geometry, defined by changing amplitudes, twisting phases, and the subtle flow of fields across the vacuum. We look at a Feynman diagram and see lines and loops. But what we are truly seeing is the quantum fabric at work, folding and unfolding according to the deep logic of nature, a logic that hides beneath particles and waves, beneath space and time, revealing that even the smallest events are echoes of something vast, intricate, and beautifully interconnected. Chapter 7. Quantum Foam and the Planck Scale. When we imagine space, even after learning of its quantum nature, we tend to visualize it as a smooth continuum, a seamless expanse of volume, stretching quietly in all directions, indifferent to scale. This view, inherited from classical geometry, persists even into much of modern physics. Space appears continuous, divisible without end, measurable to arbitrary precision. But this notion, elegant as it is, may be a grand illusion. At the very foundations of physical law, beneath the tidy abstractions of coordinates and metrics, lies a restless and chaotic structure. This is where the classical vision of geometry begins to unravel, and where the strange idea of quantum foam begins to emerge. To reach this depth, we must first confront the limits of scale. In physics, the Planck length and Planck time represent the smallest meaningful measurements of distance and duration. These quantities are derived from the combination of three fundamental constants: the speed of light, the gravitational constant, and Planck's constant. They mark the boundary where quantum mechanics and general relativity must both be applied simultaneously, and where neither, on its own, is sufficient. At scales approaching the Planck length, space-time can no longer be treated as a smooth, continuous manifold. The mathematical fabric of general relativity, which describes gravity as the curvature of space-time, relies on differentiable functions, smooth surfaces that can be bent but not torn. Quantum mechanics, on the other hand, introduces fundamental uncertainty into all physical quantities. When these two principles are brought together at extreme scales, they predict that space-time itself should become subject to quantum fluctuations, rippling with energy, distortion, and randomness. This idea was introduced by physicist John Archibald Wheeler in the mid-20th century, who coined the term quantum foam to describe the possible structure of space-time at the smallest scales. According to Wheeler's vision, the vacuum is not empty, and space is not smooth. Instead, space-time becomes a frothing sea of fluctuations, with geometry warping and twisting so violently that traditional concepts of distance and direction lose meaning. Tiny wormholes might form and vanish. Micro-black holes might flash into existence, and causal structure might momentarily fracture and reassemble. The foam is not made of particles or waves, but of uncertainty itself. Geometry pushed to its quantum limits. What does it mean for space to be foamy? In essence, it implies that geometry is not absolute, but probabilistic. Just as particles do not have definite positions until measured, the structure of space-time may not have a definite configuration at the Planck scale. Instead of being flat or curved in a determinate way, it may fluctuate between many possible configurations, each with a certain probability amplitude. This changes our entire conception of what space is. It becomes a superposition of geometries, a quantum object in its own right, with its own uncertainty, its own interference patterns, and its own wave-like behavior. These fluctuations are not currently observable with any existing instruments. To detect variations at the Planck scale would require energies many orders of magnitude beyond what any human-made particle accelerator can reach. Nevertheless, their existence is a prediction of combining quantum mechanics with gravity, and they may leave indirect traces. Some theories suggest that the foam might slightly blur the images of distant astronomical sources, or introduce noise in ultra-precise interferometers designed to detect gravitational waves. Other proposals involve modifying the dispersion of light from gamma-ray bursts, searching for hints of tiny space-time irregularities accumulating over vast cosmic distances. The idea of quantum foam is not a fully developed theory, but rather a conceptual consequence of known physics extrapolated into the unknown. It reflects the expectation that the fabric of space-time cannot remain smooth when subject to the principles of quantum uncertainty. But how exactly the foam behaves and what underlies its fluctuations remains one of the deepest open questions in theoretical physics. Various candidate theories of quantum gravity attempt to explain or formalize this structure. Loop quantum gravity, for instance, proposes that space is fundamentally discrete, composed of tiny loops or spin networks that define volumes and areas in quantized units. In this view, space is built from a combinatorial structure, and its continuum appearance at large scales arises from averaging over many such quantum elements. The quantum foam, in this interpretation, is a manifestation of the microscopic topology of these spin networks, constantly rearranging as the underlying quantum state evolves. String theory, in contrast, proposes that what we perceive as particles are actually one-dimensional strings vibrating in higher dimensional spaces. At the Planck scale, these strings and their interactions generate the geometry of space-time itself. The foam, from this standpoint, may correspond to fluctuations in the configuration of these strings and the branes they connect to. While these approaches differ in detail, they share a central theme, that the apparent smoothness of the universe is an emergent property, and that beneath it lies a restless sea of quantum possibilities. Another way to understand quantum foam is through the path integral formulation of quantum gravity. In this framework, developed by Feynman and extended by others to gravity, the probability amplitude for a space-time configuration is obtained by summing over all possible geometries, weighted by their action. Each geometry contributes to the total quantum state, and the result is not a single well-defined structure, but a weighted ensemble of potential universes. The foam is the result of this sum, a probabilistic mixture of spacetimes that fluctuates with wild variation at ultra-short scales, but averages out to smoothness at macroscopic distances. This interpretation lends itself to geometric intuition. At large scales, space appears continuous because the quantum foam is too fine to resolve. It is like observing a sandy beach from a distance. The surface appears smooth, even though up close it is a jumbled terrain of grains and gaps. Likewise, when we zoom into the quantum fabric of reality, the uniform grid dissolves into something unruly and probabilistic. The very notions of left and right, before and after, become indistinct. Causality itself may lose meaning, replaced by a network of uncertain transitions in a cloud of overlapping geometries. But perhaps the most astonishing implication of quantum foam is that even the topology of space may not be fixed. In classical physics, the topology of space, its basic connectedness and dimensional structure, is assumed to be stable. A donut-shaped space is topologically distinct from a sphere, and transformations between them require tearing or gluing. But at the Planck scale, if wormholes and topology changes can occur as quantum fluctuations, then the very kind of space we inhabit may not be absolute. It may be determined dynamically, shifting from one form to another as quantum probabilities dictate. In this view, the foam is not a mess of geometry, but a deeper layer of freedom. It represents the universe in its most flexible and dynamic form, a state where even the fundamental rules of arrangement are subject to chance and flux. This has led some theorists to explore topological quantum field theories, in which observables do not depend on metric structure, but on topological invariance. These models suggest that beneath geometry lies topology, and beneath topology perhaps something even more primitive: information, pattern, or relational structure without shape or scale. We have not yet probed this level of structure directly. No experiment has yet detected the foam, nor tested physics at the Planck length. But indirect paths are being explored. Some researchers look to black hole entropy and the holographic principle for clues, arguing that the quantum degrees of freedom of space are encoded not in volume, but on surfaces. Others study the entanglement entropy of quantum fields across boundaries, proposing that space-time itself might arise from patterns of entanglement in a more fundamental theory. The quantum foam may also play a role in cosmology. In certain models, the early universe emerges from a chaotic quantum fluctuation, with inflation smoothing the foam into the expansive space we observe today. Tiny perturbations in this foam, amplified by inflation, might even seed the galaxies and structures we now see. Thus, the randomness of geometry at the Planck scale may be not just a foundational truth, but a creative force, responsible for the very architecture of the cosmos. And yet, for all its complexity, the idea of quantum foam returns us to a simple and profound question: what is space? Not as we perceive it, but as it exists without us, before measurement, before experience, before scale. The answer seems to be that space, at its core, is not a passive backdrop, but a dynamic, uncertain, and perhaps unknowable entity. It shivers with possibility, thick with paths not taken, filled with fluctuations that we will never observe but that shape everything we do. We look for answers at the smallest scales, hoping to find clarity. Instead, we find foam, irregular, untamed, endlessly changing. And perhaps this is fitting. For in the smallest tremors of the universe, we glimpse not just its structure, but its freedom. Chapter 8. Loop Quantum Gravity, Weaving the Fabric of Space. As we descend into the depths of space-time, peeling back the layers of smooth geometry and continuous curvature, we eventually reach a point where familiar descriptions collapse. The framework of general relativity, so successful at large scales, treats space as a continuous manifold, curved by mass and energy. Meanwhile, quantum mechanics forces us to accept uncertainty and discreteness in how information behaves. Reconciling these two perspectives remains one of the great unfinished projects of modern physics. Among the many attempts to unify them, one approach takes a radical stance: that space itself is not smooth at all, but fundamentally granular. This is the vision of loop quantum gravity, a theory that replaces the fabric of space-time with a finely woven structure of quantized loops. Loop quantum gravity, or LQG, starts from the premise that the geometry of space should be subject to quantum laws. In general relativity, the geometry is described by the metric, a mathematical object that defines distances, angles, and curvature. In LQG, that metric is not continuous but composed of discrete units. The theory does not assume a background space in which events unfold. Instead, space emerges from the relations between quantum states of geometry with no need for a fixed stage. At its core, loop quantum gravity proposes that the gravitational field, like all other fields, must be quantized. But the field it quantizes is the geometry of space itself. The quantum states of geometry in LQG are represented by mathematical structures called spin networks. These networks consist of nodes and links, where the links are labeled by spins, discrete values associated with representations of the rotation group, which reflects the underlying symmetry of space. Each node corresponds to a chunk of space, and the links represent the adjacency and interaction between these chunks. The spin values determine geometric quantities, the length of lines, the area of surfaces, the volume of regions. In this framework, area and volume are not continuous but come in discrete packets, much like energy levels in an atom. There is a smallest non-zero unit of area, a smallest non-zero unit of volume. Below those, the very idea of geometry ceases to have meaning. This granularity has profound implications. It means that space cannot be subdivided indefinitely. At the smallest scales, there is no between two points, only a minimum quantum of distance, a unit of adjacency encoded in the spin network. As the spin network evolves, these discrete elements shift and rearrange, giving rise to the dynamic geometry we associate with gravity. Time itself in this picture is not an external clock ticking over a static grid, but a relational process, the transformation of network states from one configuration to another. The evolution of these networks gives rise to what is called a spin foam, a four-dimensional analog of a spin network, representing the history of quantum geometry across time. A spin foam can be thought of as a collection of two-dimensional surfaces that connect and intersect, like soap films evolving through time. Just as spin networks represent quantum states of space, spin foams represent quantum processes. They provide a way to compute transition amplitudes between different configurations of space, effectively defining a quantum path integral for gravity. These structures are not embedded in pre-existing space. They are space, or rather, the relational structure from which the appearance of space emerges at macroscopic scales. This view of space is deeply geometric, yet profoundly non-classical. It dispenses with the continuous smoothness of Riemannian geometry and replaces it with a discrete combinatorial structure. Curvature is no longer a property of smooth manifolds, but arises from how spin network edges and faces are stitched together. The classical notion of distance becomes an emergent property, meaningful only when many loops and nodes are aggregated into larger regions. Like the graininess of a digital image, the smoothness of classical space arises from averaging over a high density of microscopic elements. This picture stands in stark contrast to other approaches to quantum gravity, most notably string theory. In string theory, the fundamental objects are not points or loops of geometry, but tiny vibrating strings that live in a smooth, higher-dimensional space. The geometry in string theory is assumed to be continuous, and its properties are determined by how strings propagate and interact within it. Moreover, string theory requires additional spatial dimensions beyond the familiar three, often compactified into shapes so small they are unobservable. The quantization in string theory arises from the vibrational modes of these strings, which correspond to different particle types. Loop quantum gravity, by contrast, does not posit extra dimensions, nor does it depend on a fixed background geometry. It is fundamentally background independent, a term that means the geometry is not inserted into the theory from the outset, but emerges from the dynamics of the quantum states themselves. This makes LQG more in line with the spirit of general relativity, where space and time are dynamic and shaped by matter and energy. In LQG, there is no pre-existing arena. The arena is built from the relationships between elementary quanta of space. This independence, while conceptually elegant, makes LQG technically challenging. Because there is no fixed background, conventional methods of quantum field theory, based on perturbation expansions around a flat spacetime, cannot be applied directly. Instead, the theory must be built from scratch using entirely new tools. Much of the progress in LQG comes from studying simplified models, such as those with high degrees of symmetry, or from developing computational techniques to approximate spin foam amplitudes. Despite these challenges, the theory has achieved several important results. It predicts, for example, that black hole entropy can be derived from counting the microstates of quantum geometry near the event horizon. It also suggests that the classical singularities of general relativity, such as the Big Bang and the centers of black holes, might be resolved in a quantum theory, replaced by a bounce or transition where geometry remains finite. This vision of space as a woven tapestry of quantized loops offers a profound reinterpretation of reality. It suggests that what we experience as a seamless three-dimensional environment is in fact composed of discrete, relational units. These units are not atoms in the usual sense, but quanta of geometry, irreducible elements of area and volume whose relationships define the structure of the universe. If correct, this implies that geometry itself is subject to the same quantum rules as matter and energy, and that space is not a container but a consequence of deeper relational data. The implications extend beyond quantum gravity. If space is composed of quantized loops, then any field that exists within space, electromagnetic, nuclear, or otherwise, must interact with this granular structure. This could lead to observable effects at very high energies or over vast cosmological distances. Some researchers are exploring how such effects might influence the propagation of particles, potentially leaving signatures in cosmic background radiation or high-energy astrophysical events. Others are working on merging LQG with quantum matter theories, aiming for a unified picture of all interactions that honors both background independence and the principles of quantum field theory. Still, despite its promise, loop quantum gravity remains a developing theory. Its mathematical formalism is rich and intricate, and many aspects of it are still under exploration. Unlike string theory, which aims to unify all forces including the standard model of particle physics, LQG is more narrowly focused on quantizing gravity itself. Whether it can be extended to incorporate the full range of observed interactions remains an open question, but its core insight that space is not smooth but composed of quantized loops offers a compelling and scientifically grounded alternative to the prevailing frameworks. As we move further into the 21st century, these two visions, one of vibrating strings in smooth multidimensional space and the other of interlocking loops forming a dynamic quantum lattice, continue to develop in parallel. Each offers different perspectives, tools, and implications. Each reshapes our understanding of geometry and its role in physical law. Whether one, both, or something entirely new will ultimately prevail remains unknown. But in exploring them, we deepen our grasp of the universe and sharpen our intuition for what it means to exist within it. And perhaps in the end, this is the true significance of loop quantum gravity, not just as a theory, but as a way of seeing. It reminds us that continuity may be an illusion, that emptiness may be built from structure, and that the space between all things may itself be the most intricate weave of all. Chapter 9. The Holographic Principle, 3D from 2D. To most of us, space is three-dimensional. We live in a world where we can move forward and backward, left and right, up and down. The concept of volume is embedded in every aspect of how we interpret physical reality. We think of objects as having mass, occupying space, and existing within a defined region. But at the frontiers of theoretical physics, a bold and counterintuitive idea has taken root, one that suggests our perception of volume may be an emergent illusion, a projection of something fundamentally lower dimensional. This is the holographic principle, the proposition that the full description of a region of space can be encoded on its boundary, much like a three-dimensional object can be described by a two-dimensional hologram. The origin of this principle lies in the peculiar relationship between gravity, entropy, and information. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking explored the thermodynamics of black holes, which had long been thought of as simple, featureless endpoints of gravitational collapse. Bekenstein proposed that black holes should have entropy, meaning they contained internal information, and that this entropy should be proportional not to their volume, as one might expect, but to the area of their event horizon. Hawking then showed that black holes emit thermal radiation due to quantum effects, confirming that they indeed possess temperature and entropy. The entropy of a black hole, it turned out, is proportional to the surface area of the horizon in Planck units, not the volume enclosed. This result was shocking. In conventional physics, entropy, a measure of the number of microscopic configurations consistent with a system's macroscopic state, typically scales with volume, but black holes appeared to violate this intuition. The maximal amount of information that could be stored in a region of space was bounded not by how much space there was inside, but by how much surface surrounded it. This led Bekenstein to conjecture that information in any physical system is similarly constrained. Nature, it seemed, was not fundamentally volumetric, but surface-based. This idea was formalized in the 1990s with the development of the holographic principle by physicists Gerard Hooft and Leonard Susskind. They proposed that all the information contained in a region of space could be described by degrees of freedom living on its boundary, with no loss of information. This wasn't just a metaphor. It was a radical reframing of how space, time, and gravity might emerge from deeper principles of information theory. The most concrete realization of the holographic principle comes from a discovery in string theory known as the ADS-CFT correspondence. Proposed by Juan Maldacena in 1997, this duality connects two seemingly different theories: a gravity theory in a higher dimensional anti-de Sitter ADS space, and a conformal field theory, CFT, on its lower dimensional boundary. Specifically, the dynamics of gravity in a 5-dimensional ADS space can be fully captured by a 4-dimensional quantum field theory without gravity. Every particle, every interaction, and every curve of the gravitational field in the bulk corresponds to a quantum process on the boundary. In this correspondence, the extraspatial dimension is not fundamental, but encoded holographically in the physics of the boundary system. What makes the ADS-CFT correspondence so powerful is that it provides a non-perturbative definition of quantum gravity in terms of a well-understood quantum field theory. Instead of trying to quantize gravity directly, which leads to severe mathematical difficulties, the gravitational theory in the bulk is translated into a quantum theory that lives on a surface where the standard tools of field theory still work. In this way, space and gravity themselves become emergent properties arising from the entanglement structure and dynamics of lower dimensional degrees of freedom. This duality has transformed how physicists think about spacetime. If gravity and geometry can be encoded in a system without gravity, then perhaps our own universe, which we perceive as three-dimensional, is similarly encoded on some distant boundary. Though the ADS-CFT correspondence applies specifically to universes with a certain kind of negative curvature, ADS spaces, many believe the underlying principle is far more general and may apply, in some form, to our own universe. The holographic principle also offers a new way to understand black holes. In the classical view, anything that falls into a black hole is lost forever, its information swallowed by the singularity. But this idea leads to the infamous black hole information paradox, the conflict between general relativity, which allows for complete information loss, and quantum mechanics, which insists that information must be preserved in all processes. If black holes truly erase information, then unitarity, the foundation of quantum theory, is violated. The holographic principle provides a resolution. Since the entropy of a black hole is encoded on its horizon, all information that falls in could be thought of as stored on this surface, rather than being lost in the interior. As the black hole radiates and evaporates via Hawking radiation, this information could, in principle, be encoded in the outgoing radiation, though in a highly scrambled form. This suggests that the event horizon acts as a kind of information screen, preserving the quantum state of whatever falls in, consistent with unitarity. The interior of the black hole, in this picture, may not be fundamental at all. It may be a kind of holographic projection, a derived construct from surface data. Beyond black holes, the holographic principle has implications for the structure of spacetime itself. Some researchers propose that entanglement, not geometry, is the primary ingredient of the universe, and that spacetime emerges from the entanglement structure of underlying quantum systems. In this view, the strength and pattern of entanglement between quantum states determines not only the shape of space, but whether space even exists at all. If entanglement vanishes between two regions, the geometry connecting them may simply disappear. This has led to ideas such as E=EPR, a conjecture that wormholes, Einstein-Rosen bridges, are dual to entangled particle pairs, Einstein-Podolsky-Rosen correlations. This equivalence suggests that geometry itself is stitched together by entanglement, and that space-time is a network of quantum relationships, rather than a backdrop within which matter moves. In this context, geometry becomes a derived concept, an emergent property of information. Volume is not fundamental. It is computed from how information is shared and encoded across boundaries. Distance, too, is reconstructed from correlations, with closer regions being more strongly entangled. The metric tensor that defines space-time and general relativity may simply be a summary of these deeper quantum informational patterns. This shift from geometry to information challenges our most basic intuitions about the world. It reframes space not as a container, but as a consequence, something that appears when certain informational criteria are met. Some physicists now speculate that the universe itself could be a kind of cosmic hologram. Our perceived three-dimensional reality may be a projection from a distant, possibly inaccessible surface, a boundary of the observable universe, or some more abstract informational domain. In this vision, what we experience as movement through space is the result of shifts in a complex web of entangled data. Even time might be emergent, a bookkeeping device for changes in entropic relationships. The familiar world of positions and trajectories is merely an approximation, useful at large scales, but incomplete at the quantum level. These ideas remain speculative, and many technical challenges remain. Applying holographic dualities to spacetimes with positive curvature, like de Sitter space, which better resembles our expanding universe, is notoriously difficult. No exact duality analogous to ADS-CFT has yet been found for a cosmological setting. Still, the underlying insight continues to influence theoretical research across quantum gravity, cosmology, and high-energy physics. Even if the full holographic picture is not yet in hand, it offers a coherent framework in which space, gravity, and quantum mechanics coexist without contradiction. And it provides something else, a hint that what we perceive as real might be built from shadows. If the holographic principle is correct, then everything we see, touch, and measure may be encoded elsewhere. Our world, with all its volume and motion, might be a kind of optical illusion born of information geometry. The shapes we see, the space we move through, and the time we experience may all emerge from interactions that happen fundamentally on a screen we can never reach. In that light, the universe becomes not less real, but more mysterious. For if we are shadows on a distant wall, then the patterns we trace may reflect something even deeper, more intricate, and ultimately more beautiful than space itself. Chapter 10. Is reality built from geometry? Throughout the history of physics, geometry has served not merely as a tool, but as a language, a foundational framework for describing the structure of the universe. From the ordered simplicity of Euclid's postulates to the curved manifolds of general relativity, geometric intuition has consistently shaped our understanding of space, matter, and motion. But as we approach the deepest layers of physical law, a provocative question emerges. Is geometry just a way of organizing our observations, or is it the actual substance from which reality is made? In other words, could everything we see, particles, forces, fields, even space and time themselves, arise from pure geometric relationships? In ancient Greece, geometry began as the study of idealized forms, lines, circles, triangles. Euclid systematized this knowledge into axioms and theorems, laying the groundwork for centuries of mathematical development. These concepts were static and absolute, timeless truths about shapes in an unchanging space. For a long time, it was assumed that this geometry directly described the universe. But with the advent of modern physics, that certainty faded. Non-Euclidean geometries emerged, and the notion of a unique, privileged geometry gave way to a plurality of possible spaces, some flat, some curved, some twisted. In the early 20th century, David Hilbert attempted to place geometry on a firm axiomatic foundation, showing that geometries could be understood as systems of relations between undefined elements. This abstract formalism paved the way for general relativity, where Einstein reinterpreted gravity not as a force, but as the curvature of space-time itself. Matter told space how to curve, space told matter how to move. Geometry became dynamical, influenced by energy and mass, and in turn dictating the motion of planets, light, and even time itself. But this beautiful synthesis, as elegant as it was, still treated geometry as a continuum, infinitely divisible and smooth. As quantum mechanics developed alongside relativity, tensions began to emerge. The quantum world was not continuous but discrete, filled with probabilities, uncertainties, and non-local correlations. At the intersection of these two theories, where space becomes curved and quantum fields fluctuate, it became clear that a deeper structure must underlie them both. Geometry, it seemed, could not remain untouched. It too would have to become quantum. In seeking a quantum theory of gravity, researchers began to explore whether geometry itself could be quantized. Loop quantum gravity, as discussed earlier, proposes that area and volume are discrete, composed of spin networks that evolve through time. In this model, geometry is not a backdrop but a product of algebraic data, relations between loops and nodes. In string theory, geometry is encoded in the vibrational patterns of tiny extended objects, with the properties of space determined by how strings wrap around compactified dimensions. In both approaches, what we experience as geometry arises from more fundamental entities, often governed not by metric tensors, but by group symmetries, algebraic structures, and information. One particularly compelling idea is that particles themselves may not be independent entities, but geometric or topological features of space. In certain formulations of quantum gravity, particles are interpreted as knots or braids within networks of quantum geometry. These knots carry quantum numbers like charge and spin, and their topological stability gives rise to the apparent permanence of matter. This concept has its roots in 19th century physics, when Lord Kelvin speculated that atoms were knots in the ether. Though the ether has since been abandoned, the idea that material objects might be localized topological excitations of a deeper field has returned in modern form. Topology differs from geometry in that it concerns the properties of space that are preserved under continuous deformation. A coffee mug and a donut, topologically speaking, are the same. They each have one whole. If particles are topological objects in an underlying quantum geometric space, then their identity is not defined by their location or mass, but by how space is twisted and connected around them. This shift in perspective allows us to imagine a universe where everything we observe is simply the visible imprint of invisible topological patterns in a deeper geometric fabric. As these ideas evolved, the notion of geometry itself began to change. Rather than being a fixed entity, geometry is increasingly seen as emergent. In particular, it may arise from more primitive quantities like quantum entanglement. In several lines of research, especially those influenced by the ADAS-CFT correspondence, space-time geometry is shown to correlate with patterns of entanglement in a lower dimensional quantum system. In this picture, distances in space correspond to the strength of entanglement between subsystems. When two regions are highly entangled, they appear close together. When entanglement is weak, they appear far apart. Geometry, then, becomes a reflection of informational structure. This idea is striking because it suggests that what we call space might not be fundamental at all. Instead, it may be a convenient way of describing how information is organized. If so, then particles are not just topological features, they are emergent nodes in a network of relationships. Motion is not the translation of an object through a medium, but the reconfiguration of a pattern of entanglement. The laws of physics themselves might be statements about how information transforms, constrained by symmetry and causality. In this framework, geometry is no longer about shapes in space, but about connections in a system of data. This interpretation draws from quantum information theory, where the core elements are bits and qubits, units of information that can be entangled, transformed, and measured. It connects naturally to recent proposals that the universe is fundamentally computational, or that it can be described as a kind of error-correcting code. These models do not abandon geometry, but reinterpret it as the emergent structure of quantum correlations. Just as thermodynamics arises from the statistics of microscopic particles, space-time may arise from the statistics of entangled states. But even deeper possibilities remain. What if geometry itself is a limiting case of something more abstract, something not even spatial in the ordinary sense? Mathematical structures such as category theory, higher dimensional algebra, and non-commutative geometry are being explored as possible foundations for physics. These formalisms suggest that even topology may not be the final layer. Beneath geometry may lie pure relation, an ontology made not of things or even of space, but of transformations and symmetries. In this light, the history of physics appears not as a search for objects, but as a refinement of structure. From particles to fields, from space-time to information, each step has brought us closer to the realization that what we call reality is perhaps nothing more than the self-consistent pattern of how things relate. Geometry, in this context, is the grammar of those relationships, the rulebook for how structure gives rise to form, and form gives rise to experience. Still, these ideas remain speculative. While models such as loop quantum gravity, string theory, and holography provide compelling hints, none have yet produced definitive experimental predictions that distinguish them from classical geometry at observable scales. Testing the discreteness of space, probing topological matter at Planckian energies, or detecting signatures of entanglement-driven geometry will require technologies and insights that may be decades away. But the conceptual shift is already underway. We are moving toward a view of the universe where the distinction between physics and mathematics begins to blur, where geometry is not a passive stage, but an active participant in the evolution of the cosmos, where particles are not ingredients, but motifs in a larger pattern, and where the ultimate questions of existence, causality, and meaning are entangled with the very structure we use to ask them. Perhaps, then, the answer to whether reality is built from geometry depends on how we define both terms. If by reality we mean the evolving pattern of relational information, and by geometry we mean the structure that gives that pattern coherence, then the answer may well be yes. The world is not made of things, but of shape, not of substance but of structure, not of matter but of meaning. encoded, preserved, and unfolded by the hidden symmetries of space. And if that is so, then every step we take, every particle we measure, every point we define is not just an action in space, but a gesture of geometry itself, quietly drawing the contours of reality from the canvas of the unknown. Thanks for spending this time with me, friend. If you're still awake and your mind is still wandering, you're welcome to watch another journey into the mysteries of space and quantum thought. There's always more to explore. But if your eyes are already growing heavy, then rest well. May your dreams be quiet and your thoughts drift gently among the stars.